Let us now start talking about angular momentum. But before we discuss angular momentum, let me introduce something that you may not have covered in your math courses yet, and that's vector cross product. Cross product. Back in chapter 3 we learned about vector dot product. Vector dot product, if you have, what is vector dot product? To just a quick refresher here. If you have vector A and vector B, angle theta between them, the vector dot product is A dot B. It's a scalar quantity, so the answer here is simply A B cosine theta. The answer is scalar. It has no direction associated with it, and its magnitude is given by AB cosine theta. Now, if we have the same two vectors, vector A and vector B, angle theta between them, the cross product is a vector entity. So if you have vector A cross with vector B, then we end up with our answer has not only magnitude but the direction associated with it. Its magnitude is given by A B sine theta, and its direction is given by the right hand rule. Now, what is right hand rule? I'll try and do my best drawing here. I apologize for the lousy drawing, but if you take your right hand and kind of point your index finger should point in the direction of A, so that's the first vector in the cross product. Your middle finger should point in the direction of vector B, right? And the right hand rule says that the direction of A crossed with B is given by the direction in which your thumb is pointing. So if you have two, first of all, let me elaborate that the two vectors A and B can always be drawn such that they lie on the same plane. So here's our vector A, let's say, and here's vector B. Then this is our x and y. I'm sorry, this is the x and y directions, for example. Then the cross product of A and B is along the z direction, and in this case the cross product of A and B would actually be downwards according to the right hand rule. So once again, if you go ahead and position your thumb along A, so that's your thumb, using your right hand, then if you, I'm sorry, this is your index finger along the first vector in the vector cross product, then your middle finger, so this is the middle finger along the second vector in the cross product. And if you do that, you'll see that your thumb, if you're using your right hand rule, should be pointing downwards. So the cross product of A and B is towards the negative z-axis in this case. Now, if you consider B cross A, then the magnitude will still remain the same, AB sine theta, but its direction in this case would be in the positive z direction. So it will be this way. So this is B cross A as we've drawn, and this is A cross B. So it's important to note that B cross A is equal to negative A cross B. It's important which vector you take first. You're going to make heavy use of vector cross products in Physics 2102, the next section following this course. It's important that you learn it well, and you know how to apply it. So we have two vectors here. We have vector A, which is given, which can be written as axi plus ayj, and we also have vector B, which can be written as bxi plus byj. Then A cross B is equal to ax by k plus ay bx to negative k. Why is that? Because in evaluating vector cross product, I cross I is equal to 0, which is equal to j cross j, which is equal to k cross k. Now k is the unit vector along the z-axis. Similar, if you recall, we had I being the unit vector, representing the unit vector along the x-axis, j unit vector along the y-axis, and k is the unit vector along the z-axis. I cross j is equal to k. So if you have a vector along the x-axis cross producted with a vector along the j-axis, you end up with a vector along the k-axis. J crossed with k is equal to I, and k crossed with an I is a j. Now j crossed with an I is a negative k. This is when we made use of the fact that if you switch the order between the two components, then you end up with a negative answer. K crossed with j is negative I, and k crossed with I is negative j. So using these rules, then you can go ahead and evaluate the vector cross product of any vector following these identities. And what for example, if we know our A is equal to, I'm just making up numbers, 2I minus 3j, and the B vector is 4I plus 2j, then A cross B is, well, if you consider the I and the j term, so 2 times 2 is 4, I cross j is k from here, right? And then this product here is 3 minus 3 times minus 4 is minus 12, and j cross I is negative k, so that's times negative k, so that's 4k plus 12k, which is equal to 16k. So the cross product of these two vectors is a vector along the positive z direction and 16 units long, right? So once again, if you have the x, the y direction, and this is the z direction, I'll show you, write the z like that, that's the z direction, then vector A we said is 2I minus 3j. The way I've drawn my axis, that's not quite right, so let me redo it. You have, let me draw it the way we're used to, so x and a y. So vector A is 2I minus 3j, so that's a vector which is like this. This is our vector A, and our vector b is 4i plus 2j, which is, let's say, something like this, and the vector and in this case we have a cross b pointing, I have vector a cross with b, vector z is pointing out of the page, so this is a cross with b is out of the page, and it is 16 units long, so it's out of the page towards you, and it's 16 units long. Now, where do we make use of vector cross product in rotational motion? Well, we can, for example, go ahead and define torque as the vector cross product of moment of arm and force being applied. So if you have moment of arm length r, moment of arm is this is your rotation axis, the center of mass here. Moment of arm is the vector from the rotation axis to where force is being applied. So here I have force F being applied, and this vector R is the moment of arm vector. So R cross F here, if you use your right hand rule, point your index finger along R, that's the first vector. Point your middle finger along F, you see that your thumb is now pointing out of the page, which means that torque is out of the page. So the best way I can represent this is by kind of showing it with an arrow like this, is out of the page. So the direction of torque is orthogonal, is perpendicular to both R and F. The cross product of two vectors is always perpendicular to either vector. This is perpendicular to the plane in which the two vectors lie. So in the case of a rotating disk, if I do a side view, this is our moment of arm vector, that's the force vector, then torque is pointing out of the page, that's our rotation axis here, right? And we see that the magnitude of torque is given by the magnitude of the vector cross product of R and F, which is RF sine theta, but of course theta being 90 degrees, sine theta is simply 1, so that's simply RF. 90 degrees in this case. Had F been applied at an angle, then of course sine theta would not have been equal to 1. But the earlier definition of torque that I shared with you as given by RF sine theta only dealt with the magnitude of torque. To figure out the direction of torque in this we see that is out along the z direction. Now if you were to apply a force this way, if you were to apply a force in the opposite direction, then once again using your right hand rule, consider the cross product of RF, index finger along R, middle finger along F. You see that your thumb is now pointing downwards, which means that the torque due to this red force is in the negative z direction. Okay, this is not only defines the magnitude of torque, but of course the direction of torque as well. And we can go ahead and in a similar way consider, for example, the vector cross product of or moment of tangential velocity, so RV. So once again we have tangential velocity V, and this is our moment vector R. So R cross V. Now here we know that we're dealing with 90-degree angle, of course. So our rotation axis is about the center of mass of this disk. So R cross V defines not only the magnitude of our rotation, but also, well, it gives us the direction of the angular velocity. So R cross V is, what do you say, R cross V is given by RV sine of 90 degrees, and this direction is given by the right hand rule, right? Which is equal to RV and the right hand rule. Well, let's determine the direction. Well, the direction is simple. Let's do a side view. This is velocity, this is vector. R cross V has a direction in the positive z direction out of the plane of rotation. So that's the direction which is in the positive direction. And RV, this magnitude, if we go ahead and substitute, we'd shown earlier back in chapter 7 that V is equal to R omega. So this gives us R squared omega as the magnitude of this cross product of RV. So R cross V is a vector whose magnitude is equal to R squared omega and is pointing in the positive, let's call it positive z direction. Alright. Now, and omega is our angular velocity, of course, but you use the vector cross product method to determine the direction of omega. Now, if I were to take a derivative of this expression, then I end up with dt of R cross V as equaling R squared. R squared is just a magnitude, of course, d omega dt. Okay. Let me back up for just a second. What the substitution, when I made the substitution of omega is equal to RV, R is no longer the vector quantity, but is the magnitude of the moment of arm. So in a sense, this tells us that this direction z determines the direction of omega. So you can rewrite this as R squared omega. So R crossed V is equal to R squared omega, which gives us the direction for the angular velocity. So angular velocity of a rotating object is either out of the page, or if the rotation is if the tangential velocity is clockwise, then it's a negative omega, is down into the page. So this moment moment crossed with the velocity defines not only the magnitude but also more importantly the direction of omega. So taking a derivative of both sides, then as say r squared is simply a constant value here, it's not a vector. R squared, on the right hand side we have r squared d omega dt. The omega dt we had identified as angular acceleration alpha. Alright, and the cross product, or I'm sorry, the derivative of the left hand side is dr dt crossed with v plus r crossed with dv dt. Okay, now dr dt is v, so we end up with v cross v plus r crossed with, and dv dt is a, is equal to r squared alpha. Now any vector crossed with itself is 0 because well, v crossed v is equal to v squared sine of 0. The sine of 0 is 0. So any vector, any two parallel vectors, when crossed, you end up with a 0 answer. So we end up with r crossed a is equal to r squared alpha. Excuse me. So which tells us that once again gives us the direction of alpha. Once again, if you have a disk which is rotating with angular velocity omega, then if it is speeding up in its counterclockwise rotation, but here please note that omega upwards is our counterclockwise rotation and omega downwards is our clockwise rotation. So this is the positive rotation that we've talked about so far, and that's a negative sign for the rotation. So if the disk is rotating with a positive omega and is speeding up, then our alpha is also out of the page, because alpha is determined by the cross product of r and a, this being our moment vector, and if it has a tangential acceleration a in the counterclockwise direction, and alpha is out of the page, and if a is in the clockwise direction, then alpha would be in the negative alpha direction. So both omega and alpha point either out of the page or into the page, which they're both perpendicular to the plane in which the rotation is taking place. So let me rewrite this. R cross A is equal to r squared alpha, another handy expression to keep in our back pockets. Now I can go ahead and multiply this equation by mass, in which case I end up with r cross with ma is equal to m r squared alpha. Ma is force, so I end up with r crossed with force vector is equal to well, mr squared we defined as moment of inertia times alpha, and recall that r crossed with force we had defined as torque, so we end up with torque is equal to I alpha. So if you know which is the expression we derived earlier using scalar arguments, of course, but it's this vector cross product method also defines the direction. So you see that if an object has alpha in the positive z direction, that also implies that there's a net torque on the object pointing up in the positive z direction, or if alpha is negative, then there's a net torque on the object in the negative z direction. So once again, to recap, we see that angular velocity, angular acceleration, and torque, the direction for these you can obtain using the right-hand rule, and the direction for these vectors are always perpendicular to the plane of rotation. So how does this help us with angular momentum? Well, angular momentum, let's consider momentum. Momentum we defined as momentum vector as the product of mass and the velocity vector. So we can now take the moment of this, and we end up with r cross v. M is scalar, of course, so I can bring it out of the cross product. R cross P I can define as my angular momentum, is equal to mRV, m r cross v, and r cross v, as we saw just a minute ago, is equal to m r squared omega. So mr squared we had defined as moment of inertia, I, and omega takes its place. So therefore angular momentum is given by I omega. So the magnitude of it is simple to figure out. Is a product of moment of inertia and angular velocity, and most importantly the direction of angular momentum is same as the direction of angular velocity. So if you have an object which is rotating about a rotation axis like this, so here's the plane of rotation, for example, this distance r, it has mass m, angular momentum, moment of inertia is simply mr squared in this case, and its angular velocity is a vector, if it's rotating like this, is a vector out of the page in the positive z direction, and as this equation implies, its angular momentum vector, which is given by L, is also out of the page in the positive z direction. If the rotation were reversed, then the vectors would point downwards in the negative z direction, of course. Now, in studying linear motion, we've also seen that the rate of change of linear momentum is equal to force, net force being applied to the object. Similarly, if we take a derivative of this expression, we end up with dl dt is equal to I d omega dt, which is equal to I alpha, and I alpha, as we saw just a minute ago, is equal to net torque being applied to the object. Therefore the LDT is equal to net torque, just in a similar way that net force is equal to rate of change of linear momentum. Therefore we can see that when net torque is equal to 0, this leads to rate of change of angular momentum is equal to 0, that is momentum final. Angular momentum final is equal to angular momentum initial. Similarly, we had seen earlier that if net force is 0, then dp dt of course is 0, which means that momentum final is equal to momentum initial. Conservation of linear momentum when impulse is 0 and net force acting on the object is 0. So we can go about solving problems involving rotation just in the same manner that we solved translational motion problems, but rather than considering force, now we're dealing with torque, of course, and rather than linear velocity, we have angular velocity, etc.